I am Liam Dance, and this is Cosmology 501, Stars and Galaxies. So stars, mere decorations and a guide for navigators. Or maybe pinpricks in the curtain of night, letting the light of heaven through. Or mighty nuclear furnaces fusing hydrogen and helium into more complicated atoms. Or something else. We need to start far back in time. We'll pick the story up after the cosmic microwave background has been produced. Gravity is doing its thing, and clumps of matter are forming. In order of density, there are these antineutrons, N-bars that I call, helium atoms and hydrogen atoms. I'm going to give you an analogy, a glass jar. And into this glass jar we put a mixture of 30 glass beads and 70 polystyrene beads that are about the same size. So they go in this glass jar. And then, very carefully, we count out 190 grains of sand and pour those into the glass jar, and they will go through the glass beads and the polystyrene beads, and they will end up at the bottom. So the grains of sand are representing the N-bars, and that's why they are going to end up in the centre. They are the smallest and densest of the three things. The helium are the glass beads. They have 2 electrons in their lowest shell, and that makes a complete shell. So they're hard. And the hydrogen atoms, which are the same sort of size, but they are fuzzy. They only have 1 electron in their electron shell, and they're compressible and a bit like polystyrene. So the polystyrene and the glass beads, the hydrogen and the helium atoms, are sort of mixed up. I mean, there are more helium atoms in the centre and more hydrogen atoms on the edge, but they are mixed up. More and more matter is joining this clump. It's becoming compressed in the centre, and it's always in the same proportions. It's remorseless. Gravity is remorseless. The pressure at the centre of a clump just keeps rising. As the pressure builds, something has to give. And it's the hydrogen atoms. So the hydrogen atoms collapse, and they become neutrons. It takes a bit of energy to get them to go together, but they're in a situation where there's plenty of energy, lots of that compressive energy. So as soon as they collapse and become neutrons, they can then fall through and interact with the N-bars in the centre, where they will annihilate, producing high-energy photons, but leaving the kernels. This is important, so I'll go into it in a little more detail. So these neutrons and N bars, they are made up of many shells, and either these shells peel off and annihilate separately, just like the electrons and positrons that I talked about in the last video, or the neutron and the M bar interpenetrate each other completely and then all annihilate in one go. Whichever happens, we are left with the kernels, which can't annihilate. Here are kernels. You can see that they can't interpenetrate. And because they're entangled entities, they can't annihilate without all of them going. So they are proof against annihilation. They are almost immortal. The pinch of space that each of them contains is necessary for the structure of the universe. We can't afford to lose any. They are highly attracted to each other. But they can't annihilate, so most of them marry up. And become neutrinos. So a neutrino is this shape, which explains why neutrinos can have different interactions. They are the tiniest bar magnet imaginable, and start off at their maximum speed, which is close to the speed of light. Their job is to carry energy away from the star, after all. They exist in a realm below that of atoms, so they slip through the high density matter in the centre of the star as if it wasn't there. For this clump of matter is now a star. The star keeps getting bigger until the vast majority of the matter in the clump is incorporated. There is no maximum size for a star, but beyond a certain size it is not stable. As soon as the matter inflow drops off, it collapses. The larger the star, the shorter its lifespan. Let's look at the structure of a stable star, like our Sun. The primary source of energy is here, close to the core, where annihilation takes place, in some sort of pressure-sensitive way. In the centre of our Sun, it must be very chaotic. There's nothing that I have managed to think up that will create an orderly sort of energy production thing. It's just not going to happen. It's chaotic, so we don't know. But it must be in some sort of pressure-sensitive way. This is the radiative zone, where photons and kernels and neutrinos are rushing away. Here is the photosphere, where energy is condensing around those kernels, which have not married up. And that's where we produce the alpha particles, the protons, the electrons, the N bars of the solar wind. And more complicated atoms, and even simple molecules. This shell of matter, the photosphere, is in balance with the energy output of the annihilation in this way. If the photosphere starts to collapse, the pressure increases and more particles annihilate, which push it back. If the energy increases too much, the photosphere is pushed away and the pressure is released and the annihilation is damped down. The solar wind, which runs through the photosphere and takes things with it. Things that are condensed here get carried away by all this energy rushing through, the neutrinos. The solar wind spreads the influence of the sun. It reaches a balance with the interstellar medium somewhere between 11 and 28 light hours out. And the nearest star is 4.2 light years away. So this heliopause, at about a light day away from the sun, can be considered the outermost surface of the sun, analogous to the furthest reaches of the Earth's atmosphere. When a star runs out of matter to annihilate, the photosphere can no longer be supported, so it collapses. And, if it's big enough, all the matter contained in it annihilates over a very short period of time, a supernova. All the matter that is outside of this annihilation shell is thrown out and becomes a dust cloud, like the Crab Nebula. And new, smaller stars are seeded. The Crab Nebula is the result of a supernova in 1054. So, very recent and very small. Our entire galaxy was formed by the supernova of the first generation star. So, very long ago and very big. Now for a testable prediction. Some background first. Protons are produced from water, H2O, where they are usually called H+ ions. Antiprotons are produced by bombarding a target with protons, then separating them with strong magnetic fields. Antiprotons are N-bars with the positron shell knocked off. And because N-bars are in the solar wind, they are everywhere. Even the water we use to produce the protons. So if we could somehow process the water to produce both particles, which we could then guide and control, and then release close to each other, they will find each other and annihilate, producing a standard amount of energy. This could be done many times a second. A mass conversion energy generator, which could replace all the power stations we currently use, and could power a detection drive, a space drive.